So before we leave the graphs directly here for section 2.5, the autonomous models, I just wanted to say something about these pictures that you're seeing here. Because there is a way, many students don't know how to write down the polynomial form of a graph. So if you're looking at, say, a graph that looks like the following, suppose I've got something like that. Oh, let's keep going. How about like that? And just make these 2, 3, not to scale, 4, maybe -2. Okay, so this is going to be I'm going to assume that this is the graph of some polynomial. Let's say that this is x and y. Okay, the question is how do I write down the equation of this polynomial? Well, the idea here is that if the graph looks like it has a linear crossing at a point A, in this case point -2, then the polynomial can factor out the 2. So you'll see that x plus 2 is a factor of the polynomial. Similarly, because we have a linear crossing at 2, and a linear crossing I'm just leaving as kind of vaguely defined. It's a crossing that looks linear if you were to zoom in. This would be an x minus 2 factor. Here you would have an x minus 3 factor for your polynomial. Now what happens here, if you were to zoom into this picture, right, it's going to look like a parabola. And so in that sense you can actually factor out a double root. Okay? So now overall, what's the degree of the polynomial going to be? 1, 2, 3, 4, 5. So this is a 5th degree polynomial. And you'll notice that, well, let's just go ahead and write it out first. By the way, I'm kind of thinking about whether or not the 5th degree polynomial will have a positive coefficient in front of the x to the 5th or a negative coefficient in front of the x to the 5th. And so odd degree polynomials are going to have similar properties to the cubic, in that if this is going straight up to infinity after x gets large for some number, and this is going to minus infinity, then the coefficient in front of your highest term will be positive. Okay, if this had been flipped, right, then it would be negative. Okay, so in this case we could write our p of x as some constant times x plus 2 times x minus 2 times x minus 3 times x minus 4 squared. Good. And so it's kind of fun to be able to write the equation of a polynomial given a graph. So let's try another one. Suppose I've got the following polynomial. Suppose I've got something like this. Oop. In fact, let me draw that a little bit better. How about like that? So this is going to be -3, and this will be 2. Can we write what kind of a polynomial this is going to be? Try pausing and see if you can figure it out. So hopefully, now that you're back, you'll see that this is like a linear crossing, and so that means that x plus 3 is a factor. And then if you zoom into this, what's happening? If you were to zoom into this region right here, you see that you get a cubic function at 2. You don't really have the line there, right? And so this is going to be x minus 2 cubed. And so this is just kind of an estimate of your polynomial. Your polynomial, what's the degree of the polynomial? 3 and 1 is 4. 4th degree polynomial, as x goes to positive or negative infinity, our y values are going to negative infinity. So therefore it's going to be a minus k times x plus 3 times x minus 2 cubed. Good. And so this would be the equation of your polynomial. Very good. So now let's get back to our models. and think about modeling, because what's kind of nice about the models is that you can draw a picture of what you want your model to do in the y prime plane, and then you can construct the equation of the polynomial for your model. Okay, so one popular model for population is that we have an environmental threshold. At some value, let's say n. Okay, so what that means, by the way, the population is going to also have a equilibrium at 0, right? We didn't put that in our assumption over there, but okay, so what do I want my population to do if the population is between 0 and the environmental threshold? Well, I would like my population to increase until it gets to the threshold, and then it'll decrease afterwards. So what will the function look like, y prime? Well, on this side we need to be above the axis, and on this side we need to be below the axis. So if we connect the dots in a nice way, we end up with an upside down parabola. Good, so then what's the equation of this upside down parabola? P of y. We could say minus k times y, right? And then we could say y minus n there. Although let's rewrite it a little bit differently. Because the constant at the beginning the k value should have some meaning here, and so if you rewrite your p of y in an equivalent way, if you write it as minus k times y times 1 minus y over n, let's see what that means. You'll notice that it still has zeros at 0 and 0 at n, but now when y is close to 0, by the way, this is equal to minus ky plus k y squared over n. When y is close to 0, this value is small, so y prime is approximately minus k times y. Oops, I don't want that negative anymore, do I? Because I need my parabola to be upside down. Sorry about that. Let me, quick as a bunny, change those signs. Good, there we go. Now we're getting what we want. So when y is small, then y is approximately k times y, which is right in this region. And then what happens as we increase y, then the other equilibrium starts to take hold, and we end up with that situation. Good. And so this is called the logistic model. The logistic model. And we have y prime is equal to k times y times 1 minus y over n. And now we can even give some interpretations of the k and the n. K is the initial growth rate, and n is the environmental threshold. Good. And so we've just created a differential equation with an unstable equilibrium at the origin and a stable equilibrium at the environmental threshold. And so if we were to, let's go ahead and maybe plot these down here. This is kind of a template example. It's good to keep this one in mind. Right, that's n. And so if this is y prime and y, increasing, decreasing, and so what does the direction field look like? If this is t and y, right, then let me draw the solutions in red over here so you can see them. This is be one solution, this would be the other solution, equals n. Right, and what do the other solutions do in between? They're going up this way, down this way, and up this way. Oops. By the way, my solutions cannot intersect on the graph. Why is that? Oops. If they did, that would violate the existence and uniqueness theorem. We'll talk about that in a little bit. Alright, so there we go. That's how you construct a polynomial given a graph. And then we also talked about a template model for population, and that is the logistic model. Very good. Okay, so I probably talked too long about that particular topic, but it's kind of a nice one. We'll try some more examples in the next video.